I'm Jacob.
I'm Ramon. Don't try this at home.
Lab 10 was about lasers. Our first task was to build a heating lasers ourselves. To build this laser, the laser cavity goes from right here to right here to the mirror. We had to first align this alignment laser with the optical rail, and we used this laser and we inserted this mirror here, and there's a pinhole right here to make sure the laser light is all aligned correctly. And then we used tip tilt on the mirror for our coherent laser.
Okay, for part B, the laser beam is being splitted here through the beam splitter going to both detectors, and it's being analyzed here by the spectrum analyzer. Okay, these two modes on the spectrum analyzer represent, this one is the constructive interference of the modes, and this one, it's also a constructive interference but not as large as the first one. On the RF, we measure the distance between those two peaks and also the distance between the larger two peaks. The distance here between these two peaks was only 7 milliseconds, but between the larger peaks was 127 milliseconds. And with that, we're able to get that our frequency was 551 megahertz, which was very close to the stated frequency of 559. And also, we were able to find that the cavity for our laser was at 27.2 centimeters, and the casing is about 33, so 27.2 centimeters for the cavity makes sense. By rotating a polarizer, we see that all the modes have the same polarization state on the laser. Using the Fabry-Perot, we can see that as these two mirrors oscillate, the distance between them sometimes will match the wavelengths, and when they are matching the wavelengths, we will have rays going out of one of the mirrors, and it will create Haidinger fringes.
For the beam profiler, we had the beam go in here and go through this analyzer right here. And now over here it goes through and see. And we found the beam waste at these various distances using this value right here. We took the slope of that by measuring it at various distances to get a graph. Plotting beam width versus distance, we get this slope right here, 5.74, and we use that with trigonometry to determine the half angle of 1.398 millirads, and we use that to find omega naught to be 144 microns. In the case where n equals 1, r1 equals l1 equals 50 centimeters, and the second radius is infinite, we have a different scenario and described by this equation. That's the equation for each given one. So if we were to do some calculations at 0, 0, we have c over 2. Keep in mind that these are in hertz, not meters per second, but the magnitudes are the same. So if we subtract these two values right here, we get half of c. If we subtract these two, 3, 0, and 0, 0, we get 1.5 times c. If we do 1, 1, and 0, 0, we just get c.